Good morning, everyone. Welcome to today's session. I'm excited to introduce our topic, Automata Theory and Compiler Engineering. On this slide, you'll see the course title, the department, and the date. I'll also be your handling faculty for this course, Mrs. P. Girija from the Department of Information Technology. Today, we'll explore the fundamentals of automata, how they relate to compiler design, and walk through some key concepts. Let's get started. Welcome to Unit IV, where we focus on intermediate code generation. Today, we'll explore what intermediate code is and why it's essential in the compilation process. Specifically, we'll look into the concept of three-address code, which is a popular form of intermediate code. This step is crucial because it helps bridge the gap between high-level language and machine-specific code, making optimization and code generation more manageable. Keep in mind that this unit builds on earlier concepts of syntax analysis and semantic analysis, so understanding how intermediate code fits into the overall compiler design is key. By the end of this section, you'll have a clear idea of how intermediate code simplifies the translation process and improves the efficiency of generating target code. Today, I want to talk about intermediate code, which plays a crucial role in the translation process from source code to machine code. Think of it as a bridge that helps computers understand high-level programming languages. Intermediate code sits right between the high-level language that programmers write and the machine language that computers ultimately execute. It acts as a sort of universal language, making the process more efficient and flexible. By using this intermediate step, compilers can optimize code more effectively before converting it into machine instructions. This concept is essential because it helps improve the overall performance and portability of programs, aligning with our goal of understanding how computers process instructions behind the scenes. On this slide, we're looking at what happens if the compiler translates source code directly into machine code without generating any intermediate code. In that case, you'd need a full native compiler for each new machine architecture, which can be quite inefficient and cumbersome. Now, here's the interesting part. By using intermediate code, we can keep the analysis phase consistent across different compilers. This means we don't need to create a completely new compiler for every machine. Instead, the intermediate code acts as a sort of universal representation that simplifies the process. The intermediate code generator takes input from the previous phases, specifically from the semantic analyzer, and it works with an annotated syntax tree. This tree contains all the necessary information about the source code, enriched with semantic details. Once we have this intermediate code, the second phase of the compilation process, called the synthesis phase, can be tailored according to the specific target machine. So, instead of rewriting everything, we just adapt the final translation step, making the whole process more flexible and efficient. This approach highlights the importance of intermediate code in modern compiler design, especially in terms of portability and reusability across different hardware architectures. Now, let's take a closer look at intermediate representation, which is a crucial step in the compilation process. Intermediate code can actually be represented in two different ways. The first is high-level intermediate code, which maintains much of the structure and abstraction of the original source code. This makes it easier to analyze and optimize during compilation. The second is low-level intermediate code, which is closer to machine language. It provides a more detailed, hardware-oriented view, making it suitable for generating efficient machine code later on. Both representations serve different purposes and are essential for translating high-level programming languages into executable programs. Understanding these two forms helps us see how compilers efficiently bridge the gap between human-readable code and machine instructions. Today, let's talk about high-level intermediate code. This type of code representation is very close to the source language itself, which makes it quite intuitive. Because of this similarity, generating it from the source code is straightforward, and it also makes applying code modifications to improve performance much easier. You can think of it as a convenient bridge during the compilation process. However, when it comes to optimizing for the target machine, high-level intermediate code isn't the best choice. It lacks the low-level details needed for fine-tuned machine-specific optimization. So, While it's excellent for early stages and making code modifications, for final optimization, other forms of intermediate code are usually preferred. This concept ties into the overall theme of balancing ease of use with performance when designing compiler stages. All right, let's talk about low-level intermediate code. This stage is really close to the target machine, which makes it ideal for tasks like register and memory allocation, as well as choosing the right instruction set. Because it's so close to the hardware, it allows for machine-dependent optimizations, which can significantly improve performance. Intermediate code at this level can be language-specific, like bytecode for Java, meaning it's tailored to a particular language. Alternatively, it can be language-independent, such as three-address code, which is more general and flexible across different languages. Understanding this stage is crucial because it bridges the gap between high-level language and actual machine code, enabling more efficient compilation and execution. It's all about getting as close as possible to the machine's workings while maintaining some level of abstraction. So, as we look ahead to November 11th, 2025, it's a date that really symbolizes the culmination of our efforts and the progress we've made. This timeline marks a key milestone in our project, where all the pieces come together. It's important to understand that setting such a date helps us stay focused and aligned on our goals. It's not just a deadline, but a point to evaluate our achievements and plan next steps. Connecting this to the overall theme of our presentation, it highlights how strategic planning and clear timelines are essential for success. Keeping this date in mind keeps us motivated and ensures we're moving steadily toward our vision. All right, now let's take a look at Slide 9, which covers intermediate languages types. Here, we see that there are two main categories: graphical IRs and linear IRs. Starting with graphical IRs, these are representations that visually depict the structure of the program. For example, abstract syntax trees are tree-like structures that break down the program into its syntactic components, making it easier to analyze and transform. Then, we have directed acyclic graphs, or DAGs, which are similar but allow sharing of common subexpressions, reducing redundancy and improving efficiency. Control flow graphs are another type, showing the possible paths that execution can take through the program, which is crucial for optimization and understanding program behavior. Moving on to linear IRs, these are more sequential in nature. They often rely on stack-based representations, such as postfix notation, which simplifies the process of expression evaluation. Then, there's the three-address code, where each instruction typically involves at most 3 addresses or operands, often represented as quadruples. This form makes it straightforward to generate machine code and perform further optimizations. Connecting these concepts to our overall theme, these intermediate representations serve as crucial bridges between high-level source code and low-level machine code. They help us analyze, optimize, and ultimately generate efficient, executable programs. Understanding these different types allows us to choose the right IR for each stage of compilation, enhancing both flexibility and performance. Now, let's talk about intermediate languages. They can actually be many different languages, and it's the compiler designer who decides which one to use. This choice depends on what makes the compilation process more efficient or easier to manage. One common form of an intermediate language is syntax trees, which are structured representations of the program's syntax. They help in understanding the program's structure during translation. Another option is postfix notation, which rearranges expressions into a form that's easier for computers to evaluate step by step. But in our discussion today, we'll focus on three-address code, also known as quadruples. This form is very popular because it strikes a good balance. It's close to how machines operate, but isn't actual machine language yet. Quadruples are especially useful for understanding how code gets generated during compilation. They help us visualize the instructions that will eventually translate into machine code, giving us clear insight into the process. Remember, while quadruples are similar to machine instructions, they are not the actual instructions executed by the hardware. They serve as an intermediate step, simplifying the translation from high-level code to machine code.